All right, now we're going to cover chapter 8. We're only going to cover, just touch on a few aspects of this chapter. So again, follow the video. Don't rely on going through the text. You'll be learning a lot of material we don't really need, at least for Chem 104. So first we'll look at solutions and concentrations. This is actually the major part of this I want to cover. We'll in particular look at aqueous solutions because, first, most of our planet is covered by water. Our bodies are composed mainly of water. And most reactions we deal with in most labs are in aqueous solutions, or at least involved in aqueous solutions somehow or another. So it's good to introduce solutions themselves. Now, solutions are uniform or homogeneous mixtures of two or more substances. We have the solvent and the solute are the two major components, or the two major parts of a solution. Solvent is what you have more of. It's sometimes easier to see, sometimes not. So it's just the one you have more of. Solute is one you have less of. We tend to think of it as we dissolve the solute in the solvent. And we have solutions of all sorts of things. Aqueous solvents, aqueous solutions means that we're dissolving things in water. But there are plenty of other solutions. Metal alloys are often considered solutions of one metal dissolved in another, just uniform mixtures of metals. You have the gas we're breathing in now. Air is a mixture, it is a solution of nitrogen, oxygen, carbon dioxide, argon, a bunch of other gases mixed in there. So those are solutions. You can get solids dissolved in solids. You can get gases dissolved in solids. Think about soda, a glass of soda, a glass of Coke for Pepsi. It's got the solvent, of course, is water. It's got sugar dissolved in it, which is a solid normally. It's got high fructose corn syrup dissolved in it, which is a liquid. It's got caffeines and flavorings and CO2, which is normally a gas, dissolved in the water. So you have a solid, liquid, and gas all dissolved in the water. When dealing with solutions, we need to look at concentrations. So concentrations, there are bunches of ways we actually define concentrations. Everything from looking at relative masses, mass percent, part per million, parts per billion. There's molar ratios. There's mass of solute over liters or mass of solvent. There's moles of moles over moles. Lots of ways we can define solutions. But the thing to keep in mind is that solutions show us a ratio of solute to solvent in some way, or sometimes solute to solution. Slight difference there. It's got to be careful about that sometimes. But it can be based on all sorts of things. You've got to be careful that your solution matches up with what's being discussed. Now I left this in here. Don't worry about parts per million, parts per billion for this text. I do want to mention this briefly. First of all, I noticed that there's a couple errors here. This is parts per million. Then they messed up here, and this should be 10 to the 6 grams. Whenever you're dealing with, and even here, the book was kind of sloppy about that, about these units. This should be, that's actually, that one's correct. But this one should be milligrams per kilogram. Anyway, but you don't have to worry about that. I did want to point out that you'll have to deal with ppm and ppb in labs and industry, dealing with even hazardous waste disposal, toxic gas monitoring. When dealing with liquids by convention in most industries, parts per million will be the mass of solute over a million, times that of solution. So grams of solute over a million grams of solution is ppm for aqueous solutions, or ppb will be grams of solute over 10 to the 9th grams of solution. When dealing with gases, like toxic gas monitoring, making sure you're meeting EPA guidelines, ppm actually uses a different definition. It will be the numbers of solute particles over a million total particles. So that's kind of, I think this is frustrating as an instructor teaching you guys. We try to teach you to be consistent, and we use two different definitions for the exact same unit. So just wanted to point that out for you when you get in the industry. Be careful, make sure you understand the units being discussed. And you do have some anomalies here that can add to some confusion. I do want to mention molarity. This is what we deal with for the most part in labs because it makes it easy converting between moles and volume. The text, this is a really good way to confuse you. I don't see the point in having this equation for you. It's just makes things awkward. It's a memorization tool that's going to just trip things up and cause more confusion. The definition of molarity is moles of solute sorry, I didn't write very well, over liters of solution. Not liters of solvent, but liters of solution. Think if we had 20 grams of sodium chloride, want to dissolve that in a liter of water. Once we add the sodium chloride to the liter, our total volume is now more than a liter. So liter of solvent versus liter of solution are two different things. So be careful about that. In many cases, it's not that critical if you have very dilute solutions, but you'll get more experience with that when you get to 108 lab in a couple of semesters. And I'll go through some examples of this after I finish up. Just touch on some things in this chapter I just want to touch on. Dilutions, I do want to point out what a dilution is. It makes sense, but I want you to visualize what's happening here. You have a stock solution, a basic concentration, and to dilute it, think about what you do to dilute it. You're adding water. The main thing is we're not changing the total amount of the solute. Think about a glass of tea. It's too sweet for you, too strong. You add water to it. You're not changing the number of moles of sugar in that glass or the number of moles of tea particles. You're just adding water to it to make it more dilute. So every sip you take, you get less sugar in your mouth. So that's what a dilution is. So keep that in mind. I'll go through a couple of examples with this also. And this is the basic equation used for dilutions. Your initial volume times the initial molarity is the final volume times the final molarity. And really that's because if you work out units here with definition of molarity, both of these equals moles of solute. I can write here. So you're not changing moles of solute. Beginning and ending moles are going to be the same. That's where this relationship really came from. So, but anyway, I'll go through a couple of examples with that. I do want to touch on, just for a couple of minutes, electrolytes and acids and bases, at least one definition of acids and bases. Strong versus weak electrolytes, this is something you'll learn a little better in 105 and 6, but I do want to introduce that. Electrolytes are anything that causes ions to be formed in water. Water, this shows a light bulb. The water conducts electricity to power the light bulb. Water, opposed to popular belief, is really a lousy conductor of electricity. Well, I should say pure water is a lousy conductor. The problem is water is also a very, very good solvent. So it's hard to get pure water. So it tends to absorb many compounds, many electrolytes, things that create ions, and the ions are what make water conduct electricity. Even if you purify water and let it sit out exposed to air and don't even touch it, don't drop anything in it, it absorbs CO2, which forms carbonic acid, and that causes water to conduct. So it's hard to get pure water that does not conduct. But anyway, so strong electrolytes produce lots of ions in solution. By the chemistry definition, strong versus weak is a bit confusing for people sometimes, especially dealing with acids. Strong versus weak doesn't really have to do necessarily with how reactive a given acid is. But for a strong acid, it's going to fully split apart. So for sodium chloride, it's going to fully split apart from sodium ions and chloride ions. For HCl, this molecule, you'll learn later which are strong or weak acids. This is a strong acid, which means it's going to fully split apart in water to form H plus ions plus chloride ions. So you don't have any of these molecules hanging around in a beaker of water. They're all splitting apart to form hydronium and chloride ions. Versus weak electrolytes, they only partially dissolve. If you have ionic compounds that don't dissolve, those are actually weak electrolytes. And again, you'll learn next semester how to tell which ones dissolve and don't. Weak acids, this is a weak acid. Acetic acid is the major component of vinegar. In water, it produces the acetate ion and hydronium ions, but most of this acetic acid stays as acetic acid. That's why you have these double arrows here, because, and we have to often draw these in this way instead. Have an arrow, big arrow that direction and a small arrow in this direction. Meaning that some of it does go to form products, but most of it stays as a reactant. Just kind of qualitatively show that it is a weak acid. But you'll learn these definitions later. Again, I don't want you to memorize now which ones are weak versus strong. I just wanted to touch on these terms to introduce them before next semester. And I want to briefly mention acids and bases, the two most common definitions. Acids are anything that produces hydronium ions in solution. This is the same as H+. what's really happening here, just to mention, H plus in water doesn't exist as H plus. It combines with a water molecule to form this H3O plus polyatomic ion. But we use both of them. It's just easier to see write H plus, so you see that a lot. But they mean the same thing. At least H plus when it's aqueous. Bases are anything that produces hydroxy ions in solution. Well, at least these are the most common definitions of acids and bases. There are other definitions, Bronsted-Lowry, Lewis acids and bases, but I'm not going to have you guys worry about those for right now. You get to those later, and you'll learn which are stronger acids and bases later. I do want to mention a neutralization reaction just to show you. When we combine acids and bases, at least Arrhenius acids and bases, as I said, this is an acid, this is a base. They produce a salt, which is, in this case, sodium chloride. We think of as salt commonly. And water is produced also. So this is a neutralization reaction, where the acids and bases react. And I mention this because I want to discuss briefly also different ways we can write chemical equations. This is, again, the basic acid-base neutralization reaction we went over. We can also look at, and that's the basic molecular equation, or just we commonly think of as the chemical equation. We often write down ionic equations instead. This shows what ions are actually present in water. Well, hydrochloric acid is a strong acid. So it actually exists as hydronium ions and chloride ions in water. It splits apart fully. Sodium hydroxide is a soluble ionic compound, and you'll learn later all soluble ionic compounds are strong electrolytes. So it also fully splits apart to form sodium ions and hydroxide ions. So this is what's actually present for our reactants. And this can be very helpful in trying to predict what reactions take place, because all cations could react with any anion present in solution, or any anion could possibly react with any cation in solution. And so we'll use, in 1, 5, and 6 tables to try to determine what reactions might be taking place. For the product side, sodium chloride is a soluble ionic compound. You can tell because it's listed as aqueous here. Nice, easy way to tell. So it exists as sodium and chloride ions in solution. Water is a molecule. It stays as a molecule. It's not an acid or a base. And so we have all these ions present. Now look at this though. If you notice that there's a sodium ion on the reactant side, there's a sodium ion on the product side, there's a chloride ion on the reactant side, chloride on the products, and they don't actually do anything. We don't really need these guys. So to make this a little bit neater, we can take these guys out, and that leads to the next slide, which is the net ionic equation, and we can use this to really look and see what reaction is really happening in solution. So this shows the same thing. We can take our what are called spectator ions, because all they do is sit around and watch. They don't really do anything for our reaction. We really need them because we need them to get our initial reactants, but they don't take place in the reaction. They don't do anything. So you take these out, and we get what is called the net ionic reaction, or net ionic equation, where what we really have is hydronium ions and hydroxide ions are combining to form water. That's all that's happening. Even though we have all these ions present up here, a good chunk of them don't do anything. So, and this makes it neater. It makes it easier to see what's happening in the reaction in many cases, and helps us predict future reactions also. And the next video, I'll look through a little bit of practice with molarity to help you with that, and then we'll move on to the last chapter to look at heating and cooling curves.